Hi. So I'd like to start today by talking a little bit about Calculus 1. Now, a couple of little sort of caveats before I start this. This is not everything from Calculus 1. It's not everything you need to know from Calculus 1. And by far, it is not in the detail that you need to know it from Calculus 1. This is meant to be a way to sort of get you back into the subject, to remind you what you should have learned. And if you did learn it, that's great. You can say, I got that, no problem. If it's something that you're less familiar with, then you can go back and say, that's right, I need to learn that again. I'll go back to the book and look it up. So you can go back in the book to the previous sections and look up where that part was, and then you can go through it yourself. A couple of things that I just want to mention here at the beginning. Uh, our course in Calculus 1 is an early transcendental course, meaning that we introduce what are called transcendental functions early, which is the exponential e to the x and natural log of x. So those two functions are introduced very early in the course. So by the end of the semester, first semester of Calc 1, you'll have quite a bit of familiarity with those two and how the derivatives work with those two. The other thing is the inverse trig functions are also considered transcendental functions. So those are necessary to remember as well. So you will have to have known those those inverse trig functions and the derivatives of those inverse trig functions as well. So just if you did not have that in your Calc 1 class, that's fine. They are in the book that you can sort of go back and look at these and see, oh yeah, that's the inverse sine or something like that. And the way that it sort of works, mostly you just have to have it memorized and know what that derivative is. And then sort of the other side of it, you also have to then see how they got to that point. And the way they get there is just a lot of sort of trigonometric identities. And I'll go through those in this talk as well. So the first thing I want to sort of say here, there are different differentiation rules. So these are the rules that you should know. So the product rule says if you have the derivative of a product of two functions, f times g, you take the derivative of the first, you leave the second alone, plus the first, and you differentiate the second one, so the derivative of the second one. So you get f prime of g plus fg prime, and that's the derivative of that product. We also have the chain rule. This is a composition of two functions. So you have f with g of x plugged into it. The tricky part here is identifying which is the inside and which is the outside function. And that just takes practice. So you have to do a lot of these to sort of get yourself to the point where you're saying, okay, I see your inside function and your outside function. That's how that's going to work. All right. And so what you do is you differentiate the outside function and you plug the inside function in for each of the x's in your derivative. Then you differentiate the g, the inside function, multiply that by what you had before. And so that's the chain rule. And then the last one, the quotient rule. I personally don't ever use the quotient rule. What I will do is I'll actually rewrite that quotient as f times g of x to the minus 1. And so that's an exponent, that's the power of it. And so what I end up getting here is a product rule. So I get f prime g of x to the minus 1 plus f, I leave that alone, and now I differentiate the g, but the g is the inside function, the minus 1 power is the outside function. So that's really like minus 1 with g of x plugged in to the minus 2. Since you differentiate that minus 1 power comes in front, you subtract 1 from it. And then you multiply that by g prime of x. And if I do some simplification here, you'll notice that the first term has a g of x in the bottom. It needs two of them to make it sort of match the second term. I end up actually getting just the quotient rule out of that. So you're welcome to sort of do that. The nice thing about doing it this way is I don't have to worry about where the minus goes. The minus goes with the one that's in the denominator because it comes out of that exponent. Otherwise, I do have to memorize that it's low d high minus high d low divided by the square of what's below. So that's sort of the thing that if you don't remember that, again, maybe this is a nicer way to do that. And as I'm going through any of these sections, I'm going to try to give you the tips and tricks that I sort of see personally and how I understand it myself. This will possibly be different than the way the book is doing it, and that's on purpose. It's also possibly different than what you've seen in other videos online, say Khan Academy or something like that. They'll do something differently than potentially I will, but I find it to be very good and beneficial to see it in several ways kind of over and over and over again to really solidify the material in your mind. I mean, the point of all of this is not just the grade of this class, it is to get the understanding of the material so that when you move on into things like differential equations, linear algebra, Calc 3, these kinds of things, you will have the understanding that you need, not just the grade that you get, right? So that's the idea. All right. Other things that I might need to know are some basic derivatives. So basic derivatives, x to a power. You take the power in front and you subtract 1 from the exponent, so it's n, x to the n minus 1. E to the x is its own derivative. Derivative of sine is cosine. Derivative of cosine is negative sine. So each of the cos, that is cosine, cosecant, and cotangent, when you differentiate them, pick up a minus sign. Each of the regular functions, sine, secant, and tangent, do not pick up a minus sign. So it's, again, little hints and tricks that I might have. Tangent and secant are related, so they're the ones that kind of go to each other. And cosecant and cotangent are related. Again, they go to each other. And sine and cosine are related. They go to each other. So just little things that you can kind of pick up as you're working through and finding these things and saying, okay, so I can see, secant and cosecant look very similar. The cosecant comes in with a minus because it's a co, and it's a cosecant cotangent because those two are related. And that's kind of the way to go. All right. We also need implicit differentiation. So to take an implicit derivative, what we're really doing is we're thinking of like y is a function of x. And so when I differentiate y, or anything with a y in it, so say y squared, well, I do it as a chain rule. The outside function is whatever's happening to the y. The inside function is y of x. And so every time I differentiate y, I pick up y prime of x. And I'm going to suppress the x because I really don't need to keep writing that x. It actually will sort of muddy the waters and confuse things quite a bit here. So what I'll just write is actually y prime. So essentially, in practice, what I'm doing is I'm treating the y just like it's x, differentiating it, and then anytime I have differentiated something with a y, I multiply that term by y prime. So you can sort of see this. So the first term is xy squared, so it's a product rule. The derivative of x is 1. So I get 1 times y squared plus the derivative of y squared is 2y, so it gives me 2xy, and then I multiply by y prime because that term was a y term. 3x e to the y, so I get derivative of 3x is just negative 3, right? Negative 3x is negative 3. Derivative of e to the y is e to the y, but now I multiply by y prime because I've differentiated the term with y in it. Derivative of sine is cosine, derivative of sine of y is cosine of y with a y prime multiplied by it. Now I isolate that y prime term, move everything without a y prime to the other side of the equation. I factor the y prime out, and I divide to isolate and get y prime by itself. So this is really nice. And if I have to do a second derivative or a second one of these, I differentiate that term and then replace all of the y primes that I get when I differentiate that with this expression. Okay, so in this case, it's going to be very messy to get the second derivative, so I won't actually do it, but that's the idea as you're going through. Okay, so that implicit derivative is important. In particular, it's very important with the inverse function. So when I have an inverse function, an inverse of a function, the way that I calculate the inverse is I swap x and y values. So natural log of x is the inverse of e to the x. So when I take e to the x equals y, I swap x and y, and get e to the y equals x. And so what I do is I differentiate this expression with the y in it, and then isolate that term. So what I get, derivative of e to the y is e to the y times y prime. The derivative of x is 1. I divide both sides by e to the y. Oh, but wait a minute, e to the y is equal to x. So the derivative of natural log of x is 1 over x. So what I get here is the derivative of natural log of x. And so that's another thing that I will need to know. So the derivative of natural log is just 1 over x. Other ones that are important, so you can sort of see these. Again, I'm sort of thinking of them as like sine of y equals x is the same as saying the inverse sine of x equals y. I differentiate both sides of the expression with sine of y in it, get a y prime, divide, and then in this case I replace that sine of it's cosine of y, because when I differentiate I get cosine, with what it is in terms of sine of y. So remember that sine squared x plus cosine, well, let's do it with y, sine squared y plus cosine squared y is 1. So that means that sine squared y is 1 minus cosine squared y, and so on. So then you get sine of y is square root of 1 minus cosine squared y. And then I can go from there. And so it turns out that, in fact, since one of these is x, you end up with 1 minus x squared in the end of each of these things. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. Inverse of cosine is negative 1 over 1 square root of 1 minus x squared, and so on. Derivative of inverse tangent has 1 over x squared plus 1. Inverse cotangent is negative 1 over x squared plus 1. And then inverse secant has an absolute value in it, and this will sort of be dropped if you have only positive values of x. So possible. You get 1 over absolute value of x, square root of x squared minus 1. And then again, this would be inverse cosecant. The derivative is just negative 1 over absolute value x, square root of x squared minus 1. So these are all important ones to remember, and we'll kind of go from there. All right. So we did a bunch of stuff with derivatives, and that's important, and you'll have to remember all that stuff, things like finding the slope of the tangent line and the equation of the tangent line at a certain point. That's all very important stuff to be able to do. You'll end up sort of going back and through and doing that. And there is a homework assignment on MyMathLab that is not graded. It's not going to be tallied into your grade, but it's important to sort of try it. So it's all the stuff from Calc 1 that you should remember. So we then learned this sort of calculus integration stuff. And so the fundamental theorem of calculus basically says if I have a definite integral from a to b, and remember the definite integral from a to b of a function f of x is the area underneath the curve between the curve and the x-axis from x equals a to x equals b, where the top curve is the function f of x. And so that area is going to be this quantity right here. And the way that this actually works, because of the fundamental theorem of calculus, is I take an antiderivative, any antiderivative of the function f of x, plug in the top value, subtract off plugging in the bottom value, and that ends up giving me the area between the two, which is pretty kind of cool actually like that. So this is pretty amazing. It kind of maybe makes some sense if you're thinking about something like velocity. Well, the area under that is going to be the position. Sort of how much position have I elapsed, and that's the idea. And so that's a really kind of a nice thing. It's a great way to find that area. What we're going to do next is actually sort of take that area and talk about what we can do with it. That's kind of nice. All right. So then the other thing we want to talk about is then the indefinite integral. So the integral with no limits. That a and the b are the limits of that integral. So with no limits, I just take the antiderivative and I put a plus c at the end, because any time I have a constant on that, when I differentiate it, it's going to go away. So to go backwards in this equation, I differentiate, and the derivative of c is just 0. So I just get the derivative of f of x is little f of x. That's going backwards in this. And again, this capital F of x is an antiderivative of little f of x. And it's any antiderivative at all. And so that's sort of nice. Okay. So then the last thing we talked about in the book was this sort of idea of substitution. And this is where it's, again, important to find what's the inside and the outside function. This comes from the chain rule. So you can sort of see this is the chain rule applied to the function g prime. F composed with g of x. So that's a g prime in there. And so the inverse of that, or the integral of that, antiderivative of that, is just f composed with g. And so the idea is it's kind of tricky to look for that inside function. And so in practice, what we do is we take u as the inside function, and we calculate a du, which is just u prime of x dx. And then I sort of solve for dx which is to say dx is du divided by u prime of x, and I plug all of this with the u into original function. So let me just give you an example here. So what I might take here is I might take u to be e to the x. So that means that du is, again, the derivative of e to the x is e to the x, dx. And that means that dx is just du divided by e to the x. Okay, so now comes the substitution part. So I plug in u and dx into my expression here. So what I get is the antiderivative, is going to be 4 e to the 2x is like e to the x squared. So what I get there is actually u squared plus 3u minus 1. And then I'm going to leave that e to the x du over e to the x. So I replace my dx and I replace my du. You'll notice that e to the x cancels that e to the x, and so now I'm left with just something I can take the antiderivative of. So it's 4u to the third plus 3u minus 1 du. And so I get, so the antiderivative, I add 1 to the exponent, divide by that same expression. So I'm going to get u to the fourth, so it's going to be really 4u to the fourth over 4, plus 3u squared over 2 minus u, plus constant c, and then I plug e to the x back into this. And so what I will get here, oh, I just made a mistake here, sorry, that's a squared, that's a cubed, that's a 3. As I get 4/3 e to the 3x, so everybody caught that mistake, it's just basically translated from here to here with a u to squared to a u cubed. So this is really u squared, and that's a u to the third when I do the antiderivative of that expression. So I get e to the 3x, I get plus 3/2 e to the 2x minus e to the x plus constant c. And so that is my antiderivative expression there, and that's going to be what I end up getting out of this. Okay, and so we did that. That was great. The other sort of hiccup that comes in is if I have limits of integration, the other thing I do is I look at what is u evaluated at the bottom, u evaluated at the top, and then I don't have to go back and plug e to the x back in. I just plug in the u values rather than plugging in x values. So there's sort of a benefit to doing that. All right, so that's Calc 1. That's really a short intro to the whole thing and reminder of what you need to know. And so what I would expect you to do at this point is try that homework that's on there. So go into your assignments and check it out and see if you can make it sort of work for you. If it's not making sense, not clicking, please let me know as soon as possible, and we can sort of set up a time to talk about it, or we can just sort of look at it over email as well. So just let me know as you're going through your homework. If there's any time that you sort of don't get something, please let me know. Cool. So I will see you again in section 6.2.